Okay, so we got this rate graph. Our goal is to find the total accumulation of oil that's leaked out of the rig, either at a particular time or as a function, as an accumulation function. That's our goal. So, what was the first step?
To get an interval of x
Okay, so we're going to pick an interval of x, and what's the purpose of that?
to get the given change in y for that interval, because we can't do actual.
So, like, pick an interval width. Okay, and so why are we breaking this up into intervals? Why are we breaking this up into intervals? Wow.
It's easier to work with because each interval is a constant rate.
Okay, right. So we're going to break this up in intervals so that we can put a constant rate in each interval, right? And so let's kind of, as we go through the steps, let's actually kind of do it. You didn't have to do it for the quiz. You just had to outline the steps. But let's do that. So the reason we're doing that. So how about point 3? Is it fair? Can we make our interval point 3? So this would be breaking it up into intervals. I'm actually going to change that and do red because that's on the next slide. So we'll say the intervals are marked off by these red dots, okay? And so we come here and so we want to have a constant rate. So in that first interval, the rate is changing. We want a constant rate. And why do we want a constant rate? Is this a counter here? This is counter, right? Why do we want a constant rate in that first interval? Instead of using the changing rate.
So, calculate amount of oil loss.
Right, because if the rate is changing, it's difficult, if not impossible, to figure out how much oil has been lost. But if we have a constant rate, we know all about constant rate of change, right? We're experts. So the question is, where am I going to put that constant rate? What about at 10? Can I put that constant rate here at 10 meters cubed per day? Would that be? Okay. What about 30? What is there? Is one better than the other? 10 or 30? 30 is a lot closer. What's our goal in creating this constant rate? What's the goal of creating this constant rate, Kevin?
Are you asking what's the next step? Or like,
No. So I have to choose what constant rate I want to pick.
well, you want to pick it. So pick something that corresponds to the x value. So like on the graph that corresponds to the actual x. That increment of x that you can pick.
The increment of x. The increment of x is 0.0. We're doing 0.03. So
the y value corresponds to the increment of x value. So this is y value 0 and 0.1.
Okay, so what I heard you say was that we're going to pick a constant rate, and you were relating it to something to do with the increment or the x value.
Which side of the interval? n.0 or 3?
Oh, I'm asking a more general question. How are we going to pick a constant rate? What's our goal in picking a constant rate? To do what? Christian?
So we can create a constant rate in a function that has a changing rate of change. So it's like,
Okay, so why not here? Why not here? Why not here? So I'm trying to. What's the point of, or what's the goal in picking a constant rate?
a constant rate that at least corresponds with one of the values in the interval.
What kind of value?
Like the corresponding value of the x interval has that same value for the y.
Right. We're trying to mimic the rate. This is the whole point of doing a constant rate. We're trying to do a constant rate that kind of mimics what the actual rate is in that interval. Okay? So I'll do it in blue. So now we have a systematic way of doing that. We have a systematic way of kind of trying to mimic or pretend, create a pretend constant rate that's trying to match this rate. And how do we do that, Brent? Yeah, right. So here's a line.
Or the line closest to the rate that you chose to start at. So like you chose to start on the left-hand side.
Okay.
So you would choose at 0, maybe 28. So
This one
then
here?
The interval between 0 and 0.3, you're using that rate.
So he's saying in between 0 and 0.3, we're going to use that rate. Just like that. And so this thing is flying out to the right. So this is kind of like it's a right step. Is that right? It's a right step because it flies out to the right. This is a common, I'm pointing that out because a common mistake students think. So what kind of step is it? Left, because it's based on the rate at the left end of the interval. So don't fall into that trap of the flag is flying to the right, so that's what we're going to call right. No, we're calling this left because it's based on the one at the left. Okay, question?
Why do we use left step and right step as opposed to not taking the slope from the beginning of the slope and the end, determining an average slope?
So you want to kind of average it out?
Yeah, like take the slope from the beginning point at 0 and the slope at the end point at 0.3, the two y values, and get an average. Wouldn't that yield a better result?
Initially it will. Initially it will, but it's more work, right? So you're doing to get that value, you're doing more work each time. So you're right. So with wide intervals like that, it would give a better result, but you're paying for it. You see, you're paying a little bit more. But we're going to see that coming. This would in the end will give the same result as that one. Okay, so that's kind of coming. That's a good question. All right, so next interval then. Next interval, we look at the left hand, the function value at the left hand end. Same thing. Every interval we're taking okay, and so let's continue our story. We pick an interval with, and then what do? We create constant rates in each interval. That form a, is this the word they're using in the reading, pretend?
Yeah.
Yeah, that form a pretend rate function. And we like this pretend rate function better because, Peter, why do we like this rate function? Or Aaron, do you want to answer that?
I was just gonna say it helps us give a more accurate graph than trying to do. If we try to do it into the actual like specifics of it, then we get like a more accurate graph that doesn't look as much as what it could be if we did this on pretend rate.
So what I heard you say was creating a step function makes it more accurate. Is that what you're saying?
A little more, but it's not. It's more practical, I think.
Yes, that's true. It's more. How is it more practical? That was my question. Chloe, you want to answer that?
It's not more accurate, it's just easier to calculate. So instead of finding each individual rate for every single point, which would be an infinite number of points, brackets allow you to calculate a rate for a specific interval, assuming that it's pretty much like an average over that interval. So it just makes it easier to calculate, it doesn't actually make it more accurate.
And what makes it easier to calculate? What makes it easier, Jonathan? What makes it easier to calculate?
Because it's a constant rate.
Right. The whole point is, with a changing rate, we don't have mathematics to come up with an accumulation if the rate is continually changing. But at a constant rate, we know that change in oil leaked is what? It's the rate times how much time goes by, right? So, constant rates, and then what's the next step? We're going to use K delta X to calculate. What does it calculate? Right, bits of oil, or bits of volume. That's accumulating. Yeah.
What are the units on like the y-axis and x-axis? The x-axis
Okay.
is time and then y is m cubed.
Yeah, it's a rate function. Yeah, so I'm giving you the rate. So I'm giving you the rate at, so this is rate,
That's right.
right? So because it's a graph of meters cubed per day. That's right, that's right. Okay, and then from that we can set up an accumulation function. At this point, it's just a table. So we've got X is number of days, and then we'll call V for amount of oil. All right, so how do I calculate in the first, so how much oil has spilled at time 0? So when the oil starts leak, at the moment that it starts to leak, how much oil do we have spilled? 0, right? Okay, so then now we can figure out how much oil there's been after 0.3 days. How do we do that? Janae?
We can use the constant rate or not. Step rate. That
Okay.
should be
And what will it be? Can you do it?
so that-
Yeah, sure. Any estimate? Yeah. You want to say 29? 29? So K delta X, right? K delta X gives delta Y. So how much oil has accumulated? Someone crank that out? Someone got a calculator? Or we should be able to do that. What's that? 29 times 3? 8.7? Okay, next one. So we get, then the next time we also get 8.7. Is that right? What do you think? Why not? Why don't you get 8.7 again?
Rate change.
We're going to get more or less? Less, because the rate now is 20, right? So after 0.6, is that a good estimate? Yeah. So after 0.6 hours, the amount will be, is a 6. So this will be 6. Is that right?
No.
No, yeah, we're creating the accumulation function, right? So that 6 is not the new volume, total volume, it's the change, right? So this volume would be 14.7. Where does that come from? The previous amount plus the change in Y, which was our 6. And we could keep going like that. And so this was our goal, an accumulation function. So this table represents that function. We can look and say after so many days, we've got so much oil accumulated. Okay, there's some problems with that. What are some caveats or disadvantages to what we've created? What do you think? David?
Shouldn't the initial value start off at 29?
Okay, so is this saying the initial value of oil is 29 meters cubed?
No.
No. So you got to really keep track of what is your y-axis quantity in this graph. What is it? Is it amount of oil?
No, meters cubed per day.
It's the rate. And it's the rate since, and the x is the time since the leak started.
Okay.
So at time 0, how much oil? None. So at time 0, it bursts, right? Or something breaks, and then the oil starts flowing out, initially at this rate of whatever, 29 meters cubed per day. Okay? So does that make sense?
Mm-hmm.
All right, so problems, issues with this table as our function. There's a couple, or at least 2. Peter,
It's not very accurate
why not?
because while the graph is going downward, the steps are staying the same, so it's not accounting for that drop.
Okay, so is it saying that more oil is leaking or less than actual? So yeah, so we're with our constant, in this case at the beginning anyway, it's really giving us values that are too big, right? Too much oil, because those constant rates are all greater than the actual changing rate. You see? So that's one good thing. What else is problematic with it? Brian, any ideas?
No.
Okay. Shannon,
Typically, well, we estimated 29.
what's that?
We estimated 29, so it's not like that.
Yeah, excellent. So we eyeballed off these constant rates. So there's another kind of place for error in this. Good. What else? Right, so that goes back to another reason why this step function is not the real rate function. Ross?
It's tedious to work out every single step.
Yeah, it's sure a lot of work. And then it's a lot of work, and then what if we want, so now what if I want to know, I'm going to have 0.9 and 1.2. What if I want to know how much oil is after 1.16 days? Will I have that information? I could maybe extrapolate, right? I could kind of figure it out by looking between, but I only get these very discrete points in time. So it's very limiting function for us. It's not helpful because we only can kind of get an estimate for how much oil at these very discrete points in time. With all this interval in between, we'd have to kind of do more math to further estimate, right? Does it make sense? Yeah, so it's a lot of work, and it's inaccurate for many reasons, right? It's inaccurate for many reasons. So now that we kind of have this, any questions on this overall process? Really important that we have that framework for our goal of creating the accumulation function. Because what we want now is we want a computer to do it. Computer can do it more accurately and can do it a lot faster. And then the next step with the computer will be, so how can we make our step function better? Jonathan?
Smaller steps, smaller intervals.
Smaller intervals will create a pretend function that better matches the actual function, right? The smaller you make your intervals, the better the pretend rate function will be at recreating the actual function. So, but for doing it by hand, what about smaller intervals? Doing it by hand? A lot more work, right? So you have to pay. You have to pay for it in elbow grease and mind power and very tedious work. That's another advantage to the computer. The computer can do lots and lots of calculations fast. So we're transitioning now. Today and next week is we want a computer to do this for us. Graphing calculator. We're going to set up graphing calculator to do this for us. And we talked about sliders. So with a slider, if we set it up right, we just slide the slider, and what happens? The intervals get smaller and smaller. And instantly it's giving us a better and better accumulation function as we slide, right? And no more tables and no more of this tedious work. Okay, so this is the transition we're making. Let's get the computer to do it for us. Let's use technology to do it for us. Okay, so here we are. Here's a rate function. I've picked an interval, 1.48. Okay? So what we do the rest of today and going into next week is about getting graphing calculator to do this process for us much more quickly and much more accurately. So this is what we kind of posed at the end of last class. We're asking the question, here's my current value of x. The blue is the current value of x. And the question that we were working on at the end of class was, why do we need that x value? And we're going to call it xl, x left. Okay? And so I think, and it's lots of people we kind of jumped into this activity at the end, and it was kind of like, why are we doing this? Okay? So that's a good question, right? So we need to know why we're doing this. Again, it's our first step in having graphing calculator build this accumulation function for us. Why do we need the x value? So if I move the current value of x, what happens to that x value? Now it's that one. Make it up here. Now it's that one down there.
Are we using it more as a reference?
I'm sorry?
Are we using like that? I read about more as a reference within that.
Okay, so I want you to think about it. So I'm asking the question, but I'm wanting you to think about it. So I'm just going to set it going here, and you can talk to the person next to you. Why do we need, given a current value of x, the blue one, why do we need that left value of the interval? So talk to the person next to you. Why do we need that?
X value just corresponds to
Okay, so let's have one or two of you. What do you think? Why do we need somebody new? Why do you think we need that X value, XL? Marco.
Because the X value corresponds to those big points because they're the start of the intervals.
Okay, so that's the start of the interval. That's true. So why are we interested in it? Why do we want it? Right?
Are we looking for the X value based off of that previous X value's rate of change?
Can you say more? I'm not sure.
Well, this X value is changing, and that's the X value that we're putting in.
Blue is the current X value. Could be anything we choose to put into our accumulation function.
So is that saying use the red X value's rate of change to find that X?
Use the rate of change corresponding to that X value. And that will be the rate of change for the current value of X.
Yes.
What do you think?
Yes.
People are nodding. All right, well. Keep talking. Same question. Why do we need this value of X? We're calling it XL, the red point at the left. Keep going. Okay, I'm gonna pause it. All right, somebody new. Why do we need XL?
No, that was the reason. Why?
Is that?
You just said why do we need XL?
Oh, okay, so say more.
The X value gives us the associated Y over that interval, which is why we need the mark previous to let us know.
Okay, so you're saying this X value gives us
The Y that we're using as a constant over any interval, including where you're finding your current value of X.
What do you think? What would it say? Sterling, what do you think?
I didn't understand that.
Okay. So maybe in your own words, what do you think this?
You need that X value first of all to calculate how much has been up until that point, and then you need it also to calculate that little remaining portion of the X values.
So you're looking totally at the x-axis.
Yeah.
Okay? And he's saying it's helping us get a y. He's saying it's about getting a y value. Which is it? David? It's both.
Giving us a starting point.
It's giving us a starting point of the current interval. Okay?
So, it would help us determine the change as well from wherever the current X value is.
Okay, so it's giving us how many full intervals we've had. It gives us the change up to there. Yeah, that's totally true. My intention of this animation was about what Ryan and James said. And that's really good. That's true because we need to know these things about our current value of X. We need to know how many full intervals we've had and how much extra to our current value of X. But what's being shown up here is that X value is determining what what is that x value term me about the rate of change at our current x value?
The same.
Yeah. So it gives it to us, right? So it's giving us, for that whole interval, we're going to use that x value in the rate function to get the constant rate in that whole interval, or for the current value of x. Okay? So let's do this one right here. Find XL. So can you find XL right now? The way I have it set up. So I've got an A of negative 1.3, delta X of 1.48. And currently the current value of X is, this is the current value of X up here. So start over. Don't look, if you wrote down stuff from last class, just ignore that, put that aside. Start over, get that X value. Now that we have motivation for it, right? We understand why we need it. Find it. Find the one that I'm demonstrating right now. Does anybody need that worksheet, the blank worksheet from last time? How are we doing on passing homework around? Did everyone get the homework in front of them?
I need to.
Anybody else want the sheet? Where is the homework not been? Who's in the back? Where's the other side? So any way you can, figure out any way you can to get that X value. You got it. I got you.
The way I do it.
Well, 1.3 plus.
Oh yeah. Who else needs a worksheet? Anybody else want a blank sheet? Anybody else? Let's do that. Anybody else? Molly, could you get it?
Sorry.
Okay. Jonathan,
3.16.
and how'd you get that?
Um,
What was your process?
well, I saw that it was like the third interval from the start.
Okay.
So since each change in x is 1.48, I multiplied it 3 times 1.48.
Okay.
It's 4.46, and then subtracted 1.3.
So we're going to start at our starting value and add 3 times 1.48. Agree? So let's generalize. What's the negative 1.3? Starting value. Okay, what's the 1.48? Interval width. So here, this is the kind of the complicated part of it. It's like, what is that 3? What does it represent? The number of, what kind of intervals? Full intervals. Yeah.
When you say starting value for A,
Yeah.
do you mean like starting value on the y-axis?
Yep. No, the first x value is right there. That's A is negative 1.3. Sorry if that wasn't clear. Yeah, it's where we're starting accumulating from. Okay, so this number of full intervals, how are we going to get that number of full intervals if we don't want to count? For instance, how are we going to get that number of full intervals? So let's change it now. So now I've got delta x as 0.16. Okay, and I'm going to, so we know now this is the question mark. How many full intervals? We don't want to sit there and count because I could make it even smaller. And we could go out here to x equals 15. So we need a mathematical way to get that number of full intervals. Shimmy. Okay, so but can you give me the idea of and what does that mean, x minus a over delta x? What is that all about? Do you know? Good. So if we take x minus a, that's the distance from our starting value to, is it the starting value to our desired value or the starting value to our current value of x? Current. So let me, what's that? So I'm going to make it blue, right? Because it's the current value of x, so it's the true distance from the starting point to where we are. Okay? And you want to do what with that? Divided by delta x. And that whole fraction, would, what kind of thing does that give you? Not what number, but what does it mean?
The first full interval. Like it cuts off the decimal marker.
This ratio cuts it off? So what does this ratio calculate? Right.
Is that the number of steps from point A to where we're at now?
Number of steps, okay. Can you be more specific? It's true. It's the number of intervals. Are we done? Is that it? So that's good?
Round down.
What's the problem with the value this way?
Partial interval.
Yeah, it will be including fractions of intervals, right? Including that last fraction. So you're going to get a number like, so if I do, what is it, 3.88 minus negative 1.3 all over, what's my delta x? 0.16. Look, 32.39. And why don't we don't want to multiply 32.39 times delta x, we want the number of full intervals. Okay, so you're gonna, there's, what's happening here is there's 32 and then there's a little bit more. So what's that? Right, so we need to have the previous whole value. We need the previous whole value to get rid of that little extra because we want the number of full intervals. And that's what Shannon's talking about, the floor function, right? So we take that decimal number of intervals, and if we apply the floor function, it makes that number 32. Is there a question?
Yeah. So if we were doing the right step intervals, would we have to round up?
We could, but actually if we're gonna, that's what in your homework it's gonna talk about right and mid, but you wanna base it on the left. Just take the left and think about what would you need to do to the left to get the right, or what would you need to do to the left to get the mid instead of starting over. Okay? So this is the function that we're gonna call left x. Left is the name of the function. The input is that blue x, right? The blue x is the input. And what does it output? So we're going to put a current value of x in. And what's it going to output? This left x. Christian, what will that function output?
What's it called? How many intervals, like the closest whole number intervals to that, whatever your x is.
Okay, so he says the output's going to be the number of intervals, whole number of intervals up to x. Agree with that?
Or the value, maybe it's the value of the rate of change at that x.
Value of the rate of change. Let's see, who else? What do you think? Chloe?
It's going to give you the x value at the left point where that specific bracket is starting.
So we got three different possibilities. We got the number of intervals, the x value at the start of that interval, or the rate at the start of the interval. Do you want to, which one do you think it is? Still not sure, Shannon.
I think it's the x value like at the start of the interval.
Yeah, this was our whole goal. This was our whole goal. Figuring out that we're the x value of the starting x value. So left x takes the current value and spits out the x value at the beginning of the interval. And why do we want that? What is that for?
The rate of change.
We want, right, so we want the rate of change there because that's what the rate of change of the step function at x is going to be. You see? Okay, so in building this graphing calculator file, so first of all, let's check our answer here. So did we get an answer for this? We want negative 1.3 plus 32 times 0.16. So we're saying that this is 32. So, all right, so negative 1.3 plus 32 times 0.16. 3.82. Does it look about right? Looking at the scale? Yeah. Okay, so now my next command line shows us what that is. There it is, 3.82. We got it. Okay, so look at the first command line in my file that does this animation. It's the function. Because I'm building this animation, I'm using this function for all these visuals. There it is. Left x is a plus delta x. Floor, x minus a over delta x. Okay? So in all the command lines that build up this animation, I use this left function over and over again to get the different elements that you're seeing. Yeah.
How do you type floor?
Type floor, and then the brackets come up.
Oh,
So if you type floor, they'll just come up.
okay,
Yeah.
But how delta x?
Oh, delta on a Mac is option J. Gives the delta symbol. But because it's a string, you got to use the backslashes to set it up as a parameter. I don't know what it is on a Mac, on a PC. But if you're going to use delta x as a single variable, it's a string, right? So you got to do the backslash, delta x backslash, and then it sets it up as a single variable. Okay, so now the computer, it doesn't matter how many intervals there are, it doesn't matter how small the intervals are, the computer instantly can give us that left-hand x value very quickly. What do you notice about the step function for this very small interval size? What do you see about the step function? It's doing a good job of pretending to be the real rate function. You see that? So the smaller you make those intervals, and that's this, we're just going to slide. We're just slide that interval down to very small, and we have a step function that's virtually recreating the actual rate.
How do you like keep the slide?
You did it. You're confident.
Yeah.
So we'll work on it. We'll work on it. Okay, so the homework for Monday, there's a last question to it that I didn't quite get to, so I'll make a short video, just like 3 minutes, and you watch the video, and that'll help you do the last problem on the homework, okay? Everyone gets 100 on the quiz. Keep the quiz.